Yes.
Okay, great, awesome. Thank you, Li Hong and Mark, for the invitation and for this wonderful workshop. So today I'll be talking about exploiting latent structure and bisimulation metrics for better generalization.
Sorry. This looks like the presenter view.
Oh.
Yeah, it's not the right one.
Okay.
Maybe share the screen.
Let me try again.
This one. Yeah, it worked. Thanks.
Okay, good. Awesome. Well, you got a sneak peek of my next slide. So this talk is mainly based on this paper on learning invariant representations for RL without reconstruction. And this is joint work with Rowan McAllister, Roberto Calandra, Yaron Gall, and Sergey Levin. So this work is pretty similar, at least like it is focusing on a similar problem to the talk that Claire gave. This was some follow-up work that focused more on the state abstraction setting and thinking about how we can sort of like improve on the methods that we use for learning those state abstractions. And I just want to first start out with a more low-level view at Markup decision processes. So this is just, the definition of an MDP taken straight from Wikipedia. And the thing that I want to highlight is that this is a very broad definition that doesn't really take into account a lot of the structure and additional assumptions and inductive biases that we can put in specifically about the real world. And so I think the important question to ask here is what kind of additional structure is reasonable to assume in MDPs? Because, there's no free lunch. Like, we have to assume some kind of structure in order to get good generalization. And so in the setting that we are looking at, we assume a setting where the agent sees like a Markovian high dimensional observation, which is rendered from some true latent state. And this is a very common, very reasonable assumption to make, as this is a very common setting in robotics, as RGB cameras are a really cheap way to collect a lot of information about the environment. So in this figure here, we can see sort of like a breakdown of what information in a pixel observation is relevant versus irrelevant. So here, if we have like an autonomous driving task, if the car is in the same position on the road and the road is basically the same shape and leading to the same location, then what you see in the background or what you see on the side of the road isn't going to really affect your dynamics or your reward. And so you can think of this as irrelevant information that we want to abstract away. Whereas like if you have another image shown in orange here where, the road shape is different, but everything else looks the same, even if that irrelevant information looks very similar in terms of its pixel distance, this clearly corresponds to a different state in your latent space. So it's important to think about like how far away these pixel observations are in terms of their dynamics and reward, as opposed to their pixel distance. So our goal is to generalize to new observations where the underlying MDP is the same. And so what we want to do in order to achieve this goal is to ignore irrelevant information. And so this type of generalization or sort of common sense generalization is something that current RL algorithms can't do yet. And there's been a lot of prior work in the last few years, mainly focusing on looking at empirical generalization results that show that if you incorporate small, meaningless changes in the observation space, they can cause policies to fail. So these are just some examples from recent papers that investigate generalization in pixel space of deep RL methods. And in all of these cases, there were changes that were made between the training and evaluation that humans can clearly generalize to, but so far deep RL algorithms cannot. And so in order to solve this problem, this is now, again, like a pretty similar slide to what Claire had. And so I'm really glad that Claire did such a good job at sort of explaining and defining model irrelevant state abstractions, because bisimulation is basically the same thing. Bisimulation relations are a type of state abstraction that offers like a mathematically precise definition of what it means for two environments to share the same structure. These are considered the strictest form of state abstraction, where no information that affects the transition behavior or reward is lost. And so this is just the formal definition of a bisimulation relation, which has this recursive property that just checks that under every action in your action space, that basically two states, S1 and S2, are bisimilar if their reward is the same and their transition distributions to next latent states is the same. So this state abstraction definition is really nice, and we've seen from Claire that we can get sort of like a very nice generalization guarantees from this definition. But exact partitioning with bisimulation relations is generally pretty impractical for continuous state spaces because the relation is very sensitive to small changes in the reward function or dynamics. So if your reward differs or your transition distribution differs even by a small amount, then we can't say that these two states are bisimilar anymore. But how similar they are is still important to us, right? Like we do still want to have a distinction between states that are more similar than others. And so bisimulation metrics are really nice because it basically softens this concept of state partitions. And instead defines a pseudometric space where a distance function measures the behavioral similarity between two states. So in this definition, F basically defines this iterative procedure that starts from all states being mapped to the same point and slowly separates states based on computing this distance between abstract states. And so at the end of this iterative procedure, basically F has a unique fixed point, which is our bisimulation metric for basically any value of C. The problem with this definition is that this metric is really difficult to learn because of its inherent pessimism, because it's basically considering equivalence under all possible actions. So we have this max over actions, which is very difficult to learn in practice. So we want to modify the previous definition to get rid of this max and make this, this definition more useful for control. Because in control, we only care about the behavior of states under the optimal policy. So we can modify this standard definition to be specific to a policy pi. And we can show that if pi is continuously improving, like under policy iteration, then this iterative procedure also has a fixed point, which is our optimal policy bisimulation metric. So another issue is that this requires that we have access to the generative model, like of the actual next state distribution under our NDP. And so we can get around this by just learning a generative model of the environment. But computing the empirical Wasserstein of a generative model is also difficult. Fortunately, there are closed form solutions for Gaussian distributions. And the nice thing here is that because we are learning a latent dynamics model, we can just add another sort of assumption or restriction that this model has to be Gaussian, which means that we can now use this closed form. So now this leads us to our representation learning objective. We want to learn a representation where L1 distance between any two states in that representation is a measure of their bisimilarity. And so we can do that with this objective here. So in blue, we have the L1 distance in this latent space. And in red is the definition of the bisimilarity between those two states. And so we can plug this in directly into a deep RL algorithm. And so we call our method deep bisimulation for control, or DBC for short. And here we're just using soft actor critic, but it can be combined with any RL optimization algorithm. So what we do is we sample batches of transitions from the replay buffer. We train a reward model and dynamics model in a latent space. We make a copy of that batch, randomly permute those samples. And so now we have randomly selected pairs of states with which we can update, we can train our encoder with the previous objective and update our representation space. And then in the next step, we just train our policy on top of this latent representation. So we just train soft actor critic on top. So to test out our algorithm, a lot of our empirical results are just using the DeepMind control suite. So here we just have 3 example tasks, finger spin, half cheetah, and walker walk. And so these examples are just the original rich observation settings like from DeepMind control. But we modify this to add additional visual complexity in the background. So now this allows us to have many possible rich observations that are mapping to the same latent state. And we know here that the latent state just corresponds to like the actual proprioceptive state of the agent. So we have this slightly more difficult setting where we just have simple distractors, which are these just bouncing balls in the background that don't interact with the agent. And then we have a third final, most difficult setting, which is using natural video. So here we're just using the kinetics data set from DeepMind. We use simple image processing techniques to abstract away the background and replace it with video frames. So before I get to like, the sort of like results, I just want to show some qualitative results. So here is a t-SNE embedding for walker walk in our natural video setting. And the color code here is just the predicted value from the critic. And so we can see that states with similar value are getting grouped together. But another more interesting thing is that if you take 2 random data points that are near each other in this latent space representation, we see that the agent position is almost identical, even though the pixel distance between these observations can be very different because the background is completely different. In comparison, if we look at a t-SNE of the same observations but trained with a latent representation trained with a VAE, we see that those same data points no longer map close together. So the VAE basically is completely ignoring sort of the relevant information here, which is just the agent position. So if we look at, so here on the left, we also have just videos of the policies trained with soft actor critic with our method. And we compare against a bunch of different baselines. So in orange, we have a reconstruction-based method. So this is using a pixel-wise loss. So we're not losing any information about the background. We also compare against contrastive loss. And there's been a lot of recent work in this area, which is nice because it no longer has this, like, it doesn't force that you save all of the information in the rich observation, but what it does do is it saves all information that differs between 2 observations. So even if you have 2 different observations that are of what is the same underlying state, then a contrastive loss is going to force those to have different latent states. We also compare against a recent state-of-the-art method, DeepMDP, and stochastic latent actor critic. So in the baseline setting, we see that these methods generally perform quite well, especially SLAC. But as we increase the visual complexity of the rich observation, we see that other methods that use reconstruction or contrastive methods all start to show worse performance. Whereas DBC, our method, basically has consistent performance across all settings. So this is just the results from sort of like base case generalization, or not even generalization, just sort of like performance in the single task setting across like very complex rich observations spaces. Another nice thing that we can get out of these types of state abstractions is expected generalization to new observations and rewards. So as Claire already pointed out, a bisimulation partition or model relevance state abstraction is equivalent to learning the causal feature set of this MDP. And so what this means is that if we partition these observations using the bisimulation metric, those clusters correspond to the causal feature set, and therefore, at least in the linear setting, we know that we can generalize to like those irrelevant variables taking on any other value. We don't have those kinds of guarantees for nonlinear function approximation, but we'll show empirically that we do get some nice performance. Another thing is is the type of task generalization that we can expect to see. So we also know that the causal feature set consists of all of the causal ancestors of the reward function. So what this means is that with this representation that we've learned, we should also be able to generalize to new tasks as long as they consist of a subset of the same causal ancestors. And so we'll see what that looks like in sort of the next set of experiments. So first we look at the generalization to new observations. So in this experiment, we take our method and we train first in the ideal gas environment. We freeze the representation and then train soft actor critic with that frozen representation using the natural video setting. And so we see as a comparison that that transfer actually performs slightly better than DBC being trained and evaluated on the kinetics data set. And then as sort of like another baseline, we also look at deep MDP with the same kind of transfer scenario where we transfer from ideal gas to kinetics. And we see that our method basically performs best. So for generalization to new reward functions, so the limitation that we have here, again, is that this is only going to work if the reward function has the same causal ancestors. And so what this means is if you have an agent that's learned to pick up, say, like spheres or orbs, then it's going to abstract away anything that is not, any objects that are not a sphere or orb, which won't give it reward. So if you try to use that representation and train an agent to pick up cubes instead, then we know that it's not going to be able to do that. But in DeepMind control, there are access to different reward functions that are quite similar. So specifically with the Walker agent, there's three different reward functions that we can look at. There's Walker stand, walk, and run. And so here we found that if you train DBC on Walker walk, that we can successfully generalize to stand and run. And so these two plots are just for stand and run, and we can see that if you just train soft actor critic from scratch on the pixel observation, it performs much worse. But soft actor critic trained on a frozen representation from DBC is able to learn very quickly. And this is because the latent representation that we learn has already abstracted away all of the complexity in the visual space that does not cause reward. And so we see the same sort of behavior in both stand and run. So in the final set of experiments that I want to look at is just, we want to show that these methods work well for more realistic rich observation settings like autonomous driving. So here we look at Carli, which is a high fidelity autonomous driving simulator where you can pick different routes and change things in your rendering engine, like the weather conditions and time of day, in order to change the pixel observations. So the task here is just highway progression in meters. And there's a penalty for colliding with a wall or with other cars. And the goal is for the car to drive as quickly as possible and use the brake as little as possible. So in this setting, we find that we again compare with the same baselines as we did in DeepMind control. And again, we see that our method performs best. And then we also have some driving metrics in this table that basically show more qualitative data of how we perform in comparison to the baselines. And so we have a significantly higher number of trials which succeed, where the car is able to just progress like 100 meters without crashing. It's able to progress on average many more meters than soft actor critic or deep MDP. And so there's also just other numbers relating to crash intensity, average steering, and braking. And so here again, I think it'll be really nice to just see what kind of pixel observations, where these pixel observations map to, like in the latent space. So if we take a look in a high value section of this t-SNE, what we see is really, really interesting, because here you see that the pixel observations all look completely different. They're even sort of just like completely different lighting conditions. But the interesting thing is that in all of these states, there is some obstruction on the right-hand side. And those obstructions are completely different, but they affect the agent's policy in the same way, which is that it can't change lanes to the right, otherwise it'll collide with something. The similar points sort of like in like low value states are less interesting, but they, usually the low value states are ones where they've already crashed. But we see here on the right-hand side that, again, this is all just sort of open road. And so the policy kind of treats all of these states as the same. So here are just some additional videos looking at what the latent space looks like in Carla, as well as the DBC agent point of view during an episode. The nice thing that I really wanted to point out on the left-hand side is that we have these 3 different weather conditions for the agent that are sunny, cloudy, and sunset. And so these are the exact same episode, exact same initial state and policy, but under very different, under these different weather conditions. And you can see that where they map to in the latent space it's not perfect, but at least they are mapping very close together. So to conclude, the goal was to learn lossy representations that only capture relevant information. And we can do this by learning a representation where the L1 distance is by similarity between states. And the nice thing about using this objective is also that we guarantee that we're learning the coarsest partition. We're learning the coarsest bisimulation partition, because any 2 states that are bisimilar are forced to map to the same latent state. And we also show that policy optimization on this representation improves generalization. So thank you for listening to my talk, and I'm happy to answer any questions.
Excellent. Thanks, Amy. We have a few questions. A few minutes for questions before we move on to the next part. So maybe I can start. There's a slide in the talk that I may miss the details. I remember at some point, Amy, you said that you add some background image or video to the control problem.
Mm-hmm.
Is it a static image or is it a video?
Yeah, so it's actually video. If I can just start. Okay, yeah. So so like these videos are examples like of the environments that the agents are in. So you can see in the simple distractors that the balls are just sort of slowly moving around in the background. And in the bottom case, we're actually taking YouTube videos. So these are our natural videos that and like putting the frames under each time step of the DeepMind control environment. I see.
I was thinking that if it's a static image, then there might be easier approach to identify discover irrelevant information. But yeah, this is more interesting if you have a video in the background.
Yeah, so this is very similar to, if you remember the graphical model that Claire showed in her talk, where you can think of the rich observation as being decomposed into these 2 components, like the relevant state that causes the reward and the irrelevant one. And if you remember from her graphical model, you can have arrows, like causal arrows, from like the previous irrelevant state to the current one. And so you can think of like this video setting as following, as sort of prescribing to that graphical model.
Right. How expensive is this to run the algorithm to discover the?
Yeah, it's actually a lot. So it's on par with other model-based or with other methods that learn a dynamics model. So I guess so I guess here we have like the baselines that we used. So it's a lot cheaper than stochastic latent actor critic and the reconstruction-based method, because these methods are using pixel-wise losses. So they have to have like very large decoders that map back to the original pixel space and compute that loss. Whereas our method only needs to do this in the latent space. So you only really depend on the dimensionality of your latent space. And so for these experiments, like our latent space was just 50 dimensional. So it's quite small.
I see. But what is the cost for you to get the latent space before you run it, before you use it?
So in practice, we actually, we train both things sort of like end to end together. So every time step that the agent takes in the environment, we sort of, this entire stack of things runs. So we, like after we've collected enough data in the environment to populate the replay buffer, then we select a batch. We train the dynamics reward model and representation space using our bisimulation metric objective, and then train soft actor critic on top of it. So like again, it's basically very similar to other methods like deep MDP and stochastic latent actor critic, in that you just have all of these components that are trained at every after every environment step. So yeah, so I would say it's like on par with those.
Right. Cool. Yeah. So this is cool, and it seems the problem is you have a nice solution to this problem. Could you say something about open problem? What could be next steps?
Yeah, so the downside of bisimulation metrics is that it's very tied to just a single reward function, right? Or like you're determining what is relevant and irrelevant using the reward only. So this isn't going to work well for like say a family of tasks where you have many different reward functions. It's a little bit unclear how you can sort of extend this to that scenario. A couple things that we're thinking about are doing conditional bisimulation. So this actually maps back to Jacob's talk this morning, where like we can use natural language to define this like family of tasks, and you can learn like a conditional encoder that takes in the natural language command and outputs like a representation space specific for that task. And that way this encoder can sort of can contain information for this entire family of tasks, but each representation is still going to be specific to one. Another thing is especially for like rich observation robotics, reinforcement learning might not be the best approach. And it might be that we actually want something more similar to like imitation learning or combination of imitation learning and reinforcement learning. And so we're thinking about how we can take this definition of bisimulation and adapt it to the imitation learning setting. So now instead of having access to reward that we can use to define if two states are bisimilar or not, instead we can take expert trajectories or like example trajectories and use those to determine like if two states should be considered like the same under some definition.
Cool. Yeah, thanks.
Yeah.
Awesome. So if we don't have further questions, perhaps it's time to have a break to recover from the Zoom meetings. And then in 30 minutes, we'll come back. We'll have two more talks, one from Doina Prikop, the other from Sham Kakade. Yeah, thanks again to all the three speakers this morning, and I'll see you back in 30 minutes. Thanks.